In this video, we are going to be discussing the last topic in chapter 6, which is attractive forces. So when it comes to attractive forces, understand that these forces are also known as intermolecular forces, because these forces are going to happen in between. That's what inter means, molecules. So understand that these are very relevant, okay? And one of the ones that it is observed and is really important, okay, is hydrogen bonds, okay? Hydrogen bonds, this is just a representation of a protein, which is a biomolecule that understand that the hydrogen bonding events that are occurring in its structure between this hydrogen atom and this oxygen atom, so the hydrogen bond is actually illustrated by the dotted line, is what makes this protein has its shape. So now we're going to be discussing the three different types of attractive forces or intermolecular forces that happen specifically in covalent molecules. So the first one that we're going to discuss is dispersion forces. And when it comes to dispersion forces, understand that these are the weakest out of the three that we're going to be talking about. So this weak attractions, okay, is going to happen in between non-polar molecules. I should specify that and make it clear. So this is a weak attraction that happens between non-polar molecules. But let's write a note. Dispersion forces actually exist in all molecules. Because the idea is that as long as you have electrons, you will have dispersion forces. It's just that for non-polar molecules, dispersion forces are the strongest. Now, what causes a dispersion force? Well, it's a temporary dipole. And to explain the temporary dipole, I'm just going to zoom in to the bottom of the slide. Okay? So, understand that in any atom element within a compound, we are going to have a symmetrical distribution of the electrons. But those electrons are not static. They're always moving around, moving around, moving around. So what happens is that at some point, the movement of the electrons are going to create an unsymmetrical distribution in which the electrons are going to polarize to one side of the atom, and then it's going to create a temporary dipole, because since the electrons are in one corner, then that corner is going to become partially negative, because inside the nucleus of atoms we have protons that are positively charged. We have neutrons, but remember that they don't have a charge. So mainly because of the protons, we're going to have a delta positive charge. Once this temporary dipole, okay, has occurred, which as you can see, it is illustrated in the second image, then we have two temporary dipoles. So the atom that created that first unsymmetrical distribution, and it results in a temporary dipole because it's around other atoms, and those other atoms are also going to create an unsymmetrical distribution. And the dispersion force is actually the interaction between the positive side of one atom with the negative one. And as you can see, it is illustrated by that dotted line. Remember that these are temporary, okay? These are not permanent. The minute that those electrons start circling again, okay, this dispersion force is going to go away. So understand that this goes in and out, in and out, in and out, okay? So they're temporary. Now, when you have a polar molecule, understand that polar molecules can have one of two of these attractive forces, okay? Polar molecules can have dipole-dipole attractions. And understand that only if you have a hydrogen atom bonded to anything fun, meaning fluorine, oxygen, or nitrogen, then that polar molecule can have hydrogen bonds. So as you can see here in the bottom, we have a polar molecule, HCl. HCl, as you can see, is a polar molecule, but because the hydrogen is bonded to chlorine, the dipole-dipole attraction between two HCl molecules, which is going to be occurring because the partial positive side of the molecule and the partially negative side of the molecule are interacting, is only a dipole-dipole attraction. I'm going to now give an example of a hydrogen bond attractive force, or hydrogen bonding. So let's look at two molecules of ammonia. Okay, so here we have two molecules of ammonia. Looking at the electronegativity difference between nitrogen and hydrogen, we can tell that the nitrogen is going to be delta negative. The hydrogen is going to be delta positive. Any hydrogen is going to be delta positive. In the neighboring molecule of ammonia, the nitrogen is going to be partially negative, and the hydrogen is going to be partially positive. So when we are trying to illustrate the hydrogen bonding events that are happening between two ammonia molecules, all we have to do is interact the partially negative atom through the lone pair to the partial positive atom, which in this case is hydrogen. And this is how you illustrate a hydrogen bond. Now, attractive forces actually have serious consequences in terms of the physical properties of molecules, and one of the ones that we can observe is melting points. Understand that these three attractive forces that I already talked about are present in covalent molecules. Okay. Ionic attractive forces are only present in ionic compounds. And understand that ionic is actually stronger than the ones in covalent molecules. So if I'm trying to look at what is the trend in terms of strength, the attractive forces strength are going to increase as I move from dispersion to ionic. And as you can see here, the melting point also is increasing from things that are nonpolar all the way to ionic. So all of these observations have been summarized in table 6.18 in your textbook. And as you can see, this is just illustrating what we just talked about. The only thing that you need to pay attention is that the top of the table is actually illustrating intramolecular interactions, because this is just comparing ionic compounds versus covalent. In the bottom, when it talks about in between molecules, this is referring only to the covalent compounds, okay? And these are the attractive forces or intermolecular forces that I just mentioned. And again, the level of strength, as you can see, is the same arrow that I drew in the previous slide. Now, let's understand how to do these if I have a list of compounds. So as you can see, in this problem, you need to determine the major type of attractive force that is going to be in these particles. So understand that when it comes to this, what you need to do, if you have a molecular compound, you need to draw the Lewis dot. Okay. If you have an ionic compound, then just basically by looking at it, you know that it's ionic, and that's it. So whenever we're doing the major type, meaning the strongest, you're going to choose from ionic, dispersion, dipole, and lastly, hydrogen bonds or hydrogen bonding. So I'm going to do the first four, A, B, C, and D. So looking at these molecules, letter D, I already know that is an ionic compound, so I'm going to write ionic on it. A, B, and C are going to be specifically covalent compounds. So for covalent compounds, you need to do the following. Number one, draw the Lewis structures. Okay. Number two, determine the molecular polarity. And three, determine the attractive force. In this case, the strongest. So, letter A we already did. This is hydrogen bonding. Let's deal with B and C. So for letter B, if we draw the Lewis dot for this molecule, it's as follows. Okay? To determine the molecular polarity, I know that this is a linear molecule, okay, that is polar. Then I have to tell myself, well, if I have a polar molecule, the only choices that I have for the strongest attractive force is going to be dipole, or hydrogen bonding. Because in this molecule, the hydrogen is bonded to iodine and is not bonded to fluorine, oxygen, or nitrogen, then this is going to be a dipole attraction if I have two molecules of HI. Let's do I2. The Lewis structure for I2 is as follows. Now, for I2, understand that this molecule is also linear, but it is non-polar. Because the molecule is non-polar, then that means that the strongest attractive force that it can have is dispersion. Now, understand that there is a difference if I ask you what are all the forces present in the molecule versus what is the strongest. So in this question, we're determining the strongest. So if you utilize the following table in which you put, okay, what are the forces present in non-polar versus polar? And I plot it against either dispersion, dipole, and hydrogen bonds. This is how you know how to answer a question like that. So nonpolar molecules only have dispersion forces. Okay? Polar molecules, because they have electrons, they have dispersion forces, but dispersion forces are not going to be the strongest. Because for polar molecules, The strongest are going to be dipole-dipole or hydrogen bonding. Okay? And remember that for hydrogen bonding, only if hydrogen is bonded to anything fun. Remember, fun is the elements fluorine, oxygen, or nitrogen. Okay? So, if I ask you, for example, for letter B, okay, what are all the forces present? Your answer is going to be dispersion and dipole-dipole, because those are all the forces. Okay? But if it comes to what is the strongest out of the two, remember that dipole-dipole is strongest, so that's why for letter B, that's why we wrote dipole-dipole as our final answer. So make sure that when questions come up in attractive forces, make sure to check if the question is asking for all forces or for the strongest.